Physics chapter 25 theory video 2. So we are going to talk about magnetic force on a moving charge particle. So if there is a charged particle moving in a uniform magnetic field at a certain velocity at right angles to the field, so obviously we know that there are different factors that would affect the force that the particle would experience. So then the magnetic field would have a magnetic flux density of B. So if the magnetic field strength is high, then of course the field force is also higher. We know that. Then if the charge Q on the particle, if that is higher, again the force would be higher. Then the speed v of the particle will also have a direct relationship with the force that is acting on it. Then we can obtain an equation using these three factors that would affect the force. Force is equal to BQV. That is if there is a underlying condition, that is it should travel at right angles to the magnetic field. But once again, if it is not traveling at right angles, still we would be able to find out using the sine rule, sine BQV sine theta, if it is moving at an angle theta to the magnetic field. So we have to measure the angle theta between the magnetic field and the path of the charged particle, and using that we can take BQV sine theta. So if it is at right angle, we can simply take it as BQV. But if it has an angle, then then it would be BQV sine theta. I think it would be best if we write down an equation, write down a note. When a charged particle moves through a magnetic field at right angles to the magnetic field, the force that acts upon it would depend on following factors. Number one, magnetic flux density, capital B, the charge on the particle, capital Q, the speed of the particle, simple v. As a result, the magnetic force F on a moving particle at right angles to a magnetic field would be given by F equals BQV. So obviously we obtain the direction of the force by using Fleming's left hand rule. Then F would be always towards at an angle of 90 degrees to the velocity of the particle. And also the path that would be taken by this particle will be an arc of a circle, because the magnetic field would have a force. That force would change the path of this path of the particle after it because if there is a force generated, there would be a resultant act. So therefore the path would change. If the leave a line and write, if the particle moves at an angle of theta, to the magnetic field, the equation becomes F equals BQV sine theta. So now we learned earlier that F is equal to BIL, and now F equals BQV. So we can prove that these two are relatable. Now current is the rate of flow of charge. Because of that we can write I equals Q upon T. Then if we substitute that, to f equals BIL, we will get F equals BQL upon T. L upon T is the speed V of a moving particle. So as a result, we can write F equals BQV. Right? So they are relatable. I would suggest that you make a short note out of this part, but I will give you the note, but you must remember how to derive or equate these two equations. Write down. The equation F equals BIL and F equals BQV are consistent with one another. Leave a line and write I equals Q upon T because current is the rate of flow of charge. Rate of flow of charge. When this substituted to F equals BIL, when this substituted to F equals BIL, we get F equals BQL upon T. BQL upon T. Leave a line and write because L upon T is the speed V, we can write F equals BQV. Now, if you take a single electron which has a charge of negative E, then we can take the magnitude of the force to be F equals B, the charge of E into V, because the E is going to be 1.6 into 10 to the power minus 19 coulombs. That is the charge on it. We can use this. We can use this definition to define the force on a moving charge. When there is a force acting on all electrons, we get the BIL force, BIL force. If it is when we talk about a single particle, we call it BEV force, BEV force, because it is a charge on the single electron. But if there are more electrons, then we take it as BIL force. And one important definition here, we can write this down. For an electron with a charge of negative E, the force can be taken as follows. F equals capital B simple EV within brackets E equals 1.6 into 10 to the power minus 19 coulombs. Leave a line, put a star and write down. Even with a different color, that would be better. Force F is always at right angles to the particle's velocity V, and its direction can be found using Fleming's left-hand rule. Fleming's left-hand rule. So this is Fleming's left-hand rule. I would suggest that you pause the video and draw figure 25.7 to remind you what Fleming's left-hand rule is. And after completing that, I want you to do question number 2 and 3. After doing the questions, you can pause the video and do the questions. And after doing the questions, we have to discuss orbiting charge particles. Orbiting charge particles. Now, we know that charges orbit other charges. Now, for example, if you take an atom, we now know that the electrons orbit the central nucleus. If there is a charged particle of mass m and charge q moving at right angles to a uniform magnetic field, so it is a central circular magnetic field. It will describe a circular path because the magnetic force is always perpendicular to its velocity. That is, if you take it like this, in the earlier situation, the circular meant by circular I meant radial, right? So this is always, it will be like this. then the particle moving would go in this direction. So it is always at right angles. This would be always right angles to the path. I hope that makes sense to you. Right. Then the magnetic force F would provide the centripetal force. In circular motion, you have learned what centripetal force means and what provides it. In this particular situation, it would be provided by the centripetal force would be provided by the magnetic field. The direction of the force is obviously towards the center of the circle. That is also something that you have already discussed in circular motion. So in this figure, we have a fine beam tube. So a beam of electrons is sent and it is bent around into a circular orbit by using this magnetic field. We can see that there is we can observe this beam because there is some small amount of gas in the tube. So as a result, we can observe them. Again, here a beam of fast moving electrons are produced. A beam of fast moving electrons is produced by an electron gun using the cathode anode principle that we discussed earlier. When it comes out of the ray gun, it will be perpendicular, or it has a vertical or horizontal position depending on where it is placed. However, when it enters this spherical tube, it has a uniform magnetic field. As a result, it will be bent into a circle. Because now we know that the magnetic force that is required would be provided by the equation BQV. Using this BQV, we can figure out the radius r of the orbit of a charged particle in a uniform magnetic field. So we know that centripetal force is the equation. Then centripetal force is mv squared upon r. Therefore, BQV is equal to mv squared upon r. Then to calculate r, you can get mv upon BQ. Because it is a single charged particle, we can take it as r equals mv upon BE. Instead of Q, we can use BE. Because the momentum is mv, we can write momentum P of a particle is mv. We can write an equation P equals BER. P equals BER. So from these equations, we can obtain these details. So these are things that you need to by heart. These equations and connections you have to by heart. So R equals mv upon BE shows that if the velocity is higher, R will also be higher because it has a direct relationship. If it has a higher mass, again it would go in a bigger circle because R is directly proportional to mass. However, because B is in the denominator position, it has a B and E, the charge and the strength, the field strength. Because field strength, magnetic field strength, and the charge, because they have a inverse relationship. Higher the charge as well as higher the magnetic field strength, it would have a smaller or a tighter circle. if the magnetic flux density, that is a magnetic, if there is a strong field, it would go into a tighter circle, and this is actually, if you think about it, it becomes obvious. So these ideas we have used in especially in analyzing and identify different components of different chemicals, etc., and using particle accelerators to obtain energy. As of right now, we don't use it, but in the future, there is a possibility that we would use these. So we these have a lot of practical relationships. Let's write down a note. A charged particle of mass m and charge q moving at right angles to a uniform magnetic field would describe a circular path because magnetic force F is always perpendicular its velocity. The force F provides the centripetal force and would always act towards the center of the circle. Using a beam tube, we can observe this phenomena. And it would provide us the following relationships. Write down the equation for centripetal force, mv upon r, mv squared upon r. mv squared upon r. Then write down, as a result, centripetal force equals mv squared upon r. As a result, now you know that centripetal force is what provides the force, the force that keeps it, magnetic flux density. Because of the magnetic flux density, the force generated on the charge is BQV. Therefore, as a result, BQV equals mv squared upon r. From this, r equals mv upon bq. r equals mv upon bq. Also, if the charged particles are electrons, Q is equal to E, simply Q is equal to E. Therefore, R equals mv upon BE, capital B, simple E. Then if you move this B to this side, you will get mv equals to BER, but because mv is equal to momentum P, you get P equals BER. That also you write down. The momentum P of a particle is mv. Therefore, P equals BER. Leave a line and write. From the equation R equals mv upon BE, we can understand that higher the mass and higher the velocity of the particle, radius would be higher because R is directly proportional to V and M. Leave line and right. If the charge as well as the uh, field strength is higher, the radius would lower because they have an inverse relationship. I hope you understood. We will discuss the charge to mass ratio of an electron in the next video.